Hello, everybody. Thank you for coming to my talk. My name is Joseph Batir. I'm with Petrolern. I will be talking to you about the 4 types of geothermal energy, those in quotes. We will get into that in a little bit. Thank you to Dwayne Purvis for inviting me to speak at CarbonExpo. I hope you all have been having a great time so far, and hopefully I'll be seeing you in some of the live interactive sessions, and we'll have a chance to get to know each other more. With that, let's jump into this discussion. I'm going to start off with the outline and just jump right into the punchline. What I want everybody to leave here today knowing or believing is that geothermal in some form is available everywhere. What that looks like may be different depending on where you are. And more importantly, full adoption and commercialization requires oil and gas skills, oil and gas infrastructure, and the oil and gas workforce. With buy-in from the oil and gas industry, we could have geothermal everywhere. But it really does take that. And I'm going to kind of go through multiple different ideas to show you where and how we can be applying the oil and gas skills, workforce, and infrastructure to a green energy future. I'll be going through what is geothermal, how do we know geothermal power is there, the 4 different types of geothermal that we are discussing here today, and how can we leverage oil and gas to advance geothermal energy. A quick introduction of who I am and why am I talking. I'm Dr. Joseph Batir. I went to SMU. I have a PhD. Technically, it's in geophysics. It was all focused on geothermal energy, resource characterization, and understanding large-scale tectonic and thermal processes and how that might drive things like thermal maturity models and geothermal energy and geothermal system locations. I have been working on geothermal exploration, both as part of my schooling and ever since. I've worked in multiple projects all over the US, recently finished up a project in Colombia, and all of my work for my PhD was Alaska, and I've been working with people on getting projects off the ground there ever since. This picture on the right is actually from a wellbore that I logged right outside of Haines, Alaska. So this is some of the fun stuff that you get to do when you're a geothermal geoscientist. And right now I am a senior geothermal geoscientist with Petrolern. So let's first establish this baseline knowledge. What is geothermal? I'm starting very, very simply here. Geothermal is geo, meaning earth, therme, meaning heat. So this is the heat flowing up out of the earth. And when we think about the heat flowing up out of the earth, well, the earth formed roughly 4.5 billion years ago. That process created all this energy that is now in the inner core, in the outer core, and slowly being released through the mantle. That energy in the form of heat is slowly being let go. It is coming up through the inner and outer crust, slowly working its way through the mantle, and ultimately being let out of the lithosphere or through the crust. So this is the heat from both when the earth formed, and then there is also radiogenic heat production. And all of that heat is what we are harnessing. In certain areas in the earth, this heat is more centralized than in other areas. Where it's more centralized, there are fluids that are flowing, picking up that heat, and naturally flowing to the surface at very hot temperatures. Think of volcanoes, geysers, hot springs. These are the areas we can target for traditional geothermal. But as we said, there are multiple different possibilities. So when we talk about geothermal energy, how can we use this? How can we harness this geothermal energy? Well, the possibilities really are endless. You could think of something as basic as a hot spring. This is a hot spring in the San Juan Hot Springs in California. You could go and take a bath there. You could go and warm yourself up. You could go and wash clothes. This is a very at the core of geothermal, going and enjoying hot springs. That is as simple as it gets for energy utilization. A step further, this is a picture coming from Enel Green Power. This is the Larderello geothermal power plant in Italy. This is the first geothermal system that was utilized for geothermal electricity production. This is a dry steam field, which we'll talk about in a little bit. But going from a very, very basic natural direct use into electricity production, combining the two ideas, we could have both electricity production, which is taking place in the far part of this picture, and then direct use applications, everybody bathing in this hot spring. Many of you probably know what this is. This is the Blue Lagoon in Iceland. The power plant that actually supplies all of this water for the Blue Lagoon is the Svartsengi power plant. It also produces geothermal electricity for Reykjavik. The next image, kind of thinking all of these different possibilities. So now we've got this section of sidewalk melted. Why is that section of sidewalk melted? Well, this is Klamath Falls, Oregon. In Klamath Falls, they have a low temperature geothermal resource that they utilize for district heating. In this picture specifically, we're showing the district heating, or that direct use heating that keeps sidewalks snow-free and ice-free, ultimately making it safer for people walking, making it so you don't have to throw down sand, you don't have to throw down salt. This is a direct use application. So instead of just using a hot spring as it is, now we are taking that hot spring water and we are moving that heat to a specific location where we want to use it. Another idea, and a more extreme environment, this is a picture from Chena Hot Springs in Alaska. Chena Hot Springs has a geothermal system. They generate electricity. They generate heating and cooling for all of the resort buildings. And they also have greenhouses. This is nearly in the Arctic Circle. This is up near Fairbanks, Alaska. And they have greenhouses that are producing fresh food year round. The reason this is possible is because the reason that this works is because they've got their geothermal heating and they have a low cost electricity source, that also being the geothermal. So this is another example of how you can use that direct use heat in an innovative way that is not exactly intuitive. Most people don't think about growing fresh tomatoes in the middle of Alaska in the middle of winter, but you can. And one of the things that we're going to kind of focus on today, there is also the possibility to produce geothermal electricity from legacy oil and gas fields. Some of you may know this picture. Some of you may know this area. This is the Rocky Mountain Oil Field Testing Center. This is Teapot Dome in Wyoming. That was a government-run facility, a government-owned oil and gas field. And towards the end of that facility's tenure as a government-owned facility, it started doing some geothermal testing of topside equipment and of a few other things. We'll focus on the topside equipment today and actually producing that power, but we'll talk about that. And that's one great example of geothermal oil and gas co-production, which ultimately could extend the life of late stage fields. So the whole goal of showing all of these pictures, we really have things that are as simple as relaxation, as straightforward as producing fluids and running electricity, something that is a little bit more complex, combined power generation and combined direct use, very similar to something like a combined heat and power system. And then we have innovative ideas where we can utilize lower temperature resources in very impactful, life-giving way, such as making sidewalks safer in the winter and providing fresh food in a very desolate location for certain times of the year. And of course, ways to innovate, bring in the oil and gas industry and help prolong this industry and think of it in a non-traditional sort of way. So how do we know that geothermal is there? Well, we measure it. All of you who have ever gotten a well log during your career in oil and gas, you have measured the temperature in the subsurface. The primary data source that I use when I'm doing these geothermal maps and these geothermal calculations is from bottom hole temperatures from well logs. In case you've forgotten where that is on your well log header, it's kind of towards the bottom. It's right above the circulation information. Oftentimes it says maximum recorded thermometer or maximum recorded temperature, and then you have a temperature there. Now, I originally tried to blow this up a little bit more so we could look and see what that temperature was. But if you can't tell, these are not exactly easy to read. And especially after you've made a scan of this, and then you've converted it to a PDF, and then you download it, and then you zoom in, you start to get very pixelated numbers, and you start to get degradation of the image. So that's a problem that maybe we'll talk about later, maybe we won't. If we have enough of these data points, this example coming from Crockett County, when we get enough of these, we can start looking at temperature versus depth. So in Crockett County, we've got lots of information, lots of data points that we can plot the temperature versus the depth and get an idea of what's going on in the subsurface. Oftentimes, and really, I prefer to not stop there. I try and take this one step further. So first you have the temperature that you've now collected, make some corrections, and now we can calculate what I would consider more useful values. We can calculate heat flow, we can calculate temperature at depth, and we can calculate the heat in place. So why do we want to go to heat flow and not just stop at gradient? If we look at this example, now jumping across the state of Texas over to Louisiana, this is a very good image of why heat flow and not gradient. In this temperature log, we've got this temperature log. It's fairly linear down to about 7,500 feet, maybe a little bit less, 7,000 feet. And then you see a clear change in gradient, a drop in that increasing temperature with depth. With that information, with that equilibrium temperature log, we can see that change. And now, instead of calculating something that may have looked like this straight line continuing to heat up, we know that we're going to have this lower gradient that is ultimately going to be cooler at deeper depths. If we just used a bottom hole temperature, and these are all different bottom hole temperatures near this well, if we used one of those, ultimately, any single one of those is going to give us an erroneous gradient value. They're not going to give us something that is going to properly estimate temperature anywhere besides really right in that section. I want to walk through these data points because many of you may know we often will correct the bottom hole temperature using a correction. We know that the bottom hole temperatures are disturbed from drilling. So what we'll do is we will add a little temperature to it. It is more scientific than that. There are studies that have looked at how to do that addition of temperature to estimate equilibrium temperature. This is one example where we've got a Harrison corrected BHT, which goes back to a correction made specifically for the Anadarko Basin. And notice for the Harrison correction, these temperatures still aren't even near the equilibrium temperature log. And then we have a SMU second correction. This SMU second correction was an amendment, so to speak, to the Harrison correction, where an additional add-on of heat was combined with the Harrison correction to try and increase those temperatures. Many of those still, they're closer to equilibrium, but they are not quite there. So the point in showing the bottom hole temperatures on this figure, along with the equilibrium temperature gradient, is twofold. With the BHTs, even with a correction, you may not be very close to the actual equilibrium temperature. So if we were anywhere in this upper section, even with a corrected temperature, we're not in the ballpark for knowing what the temperature is. At the bottom of the well, we have a better estimate, but the problem is now if we try to extrapolate temperature deeper, we're going to be extrapolating a line that has a higher gradient than if we were to extrapolate the correct equilibrium geothermal gradient. So I've kind of talked around this figure quite a bit. I'm trying to lay out why we need to calculate heat flow and not just gradient. To put it very clearly, gradient is going to change with every lithology, whereas heat flow is quote unquote constant with depth. So within the depth of measurement for heat flow should be constant within error measurement. And once we have that heat flow measurement, we can then calculate temperatures that are deeper. For this figure and for this area in Louisiana, I want to point out these temperatures that the deepest wells have reached really should be about 135 Celsius, maybe around 265 Fahrenheit, 270 degrees Fahrenheit. That would be hot enough to run a low temperature system. We're going to get into that in a bit. But the problem is, if we're estimating based on this upper section, by that depth, we may think we're going to be at 300 Fahrenheit. 300 degrees Fahrenheit is significantly different than 270 Fahrenheit or 260 Fahrenheit. We're in a different type of power production scheme at that point. This is why it's so important to calculate heat flow and then use that heat flow to accurately calculate the temperature at your depth of interest. So where does geothermal exist? This is a map that I was part of making. This is the geothermal map of the United States. You can see where there are higher amounts of data just by the variability in the mapping. And you can see based on the scale here, the areas that have a high heat flow and the areas that have a low heat flow. Generally speaking, areas with higher heat flow are going to be more prospective for geothermal energy. Areas with lower heat flow would be less prospective for geothermal energy. I am going to flip that a little bit. I'm going to make the case that really geothermal is everywhere, but not in this traditional way that you may have heard about it before. So high temperature is geothermal energy. Low temperature can be geothermal energy. And in fact, everywhere we can create what we call synthetic geothermal. And I will be talking about that soon. So you see all these stars that just populated on this map. These are all locations where there has been some level of federal funding going into these projects, going into exploring for geothermal energy. Projects that I have worked on or have peer reviewed include in the Illinois Basin, over in the Appalachian Basin at Cornell University and West Virginia University, areas in Texas, in East Texas, in South Texas and near Houston, areas in the Williston Basin. So there's a lot of this. And then, of course, the Western US that is traditionally known for having geothermal energy. Looking at this map, I think it's important to point out that there are geothermal projects across the US. They are targeting different resources, different temperatures, and different ways of utilizing that power, that geothermal energy. And the way that all of these can be successful is through innovative thinking and transfer of knowledge using oil and gas skills, oil and gas infrastructure, oil and gas technology that combined with the geothermal industry and the geothermal inputs to really understand what's going on here and how to best utilize the resources available. So now let's actually talk about the namesake of this presentation, the quote unquote 4 types of geothermal. So why do we say 4 types of geothermal? And why is it in quotes? Well, there's different ways to characterize geothermal. Here, what I'm saying here, and I think what is helpful is talking about different utilization types. So that's why we've got type. There's another way you could think about it as, so the first way you could think about it is geothermal heat pumps, direct use applications, and electricity generation. Those are 3 different types. The types we're going to talk about here are heating, cooling, binary fluid, steam power generation, and direct steam or flash steam generation. I am going to talk about geothermal heat pumps right now. That is a system for heating and cooling. Really what that's doing is using the nearest top of the subsurface as kind of this thermal energy insulator. These temperatures where you can utilize geothermal heat pumps vary from 4 to 100 degrees Fahrenheit. Geothermal heat pumps are something that you can use everywhere. There are geothermal heat pumps used in places like Norway and Finland and Sweden. There are places in Canada that utilize geothermal heat pumps, and there are companies that are exclusively geothermal heat pump installers. This is a commercial ready technology that is actively being put out there into the world. This can be coming from the, I guess you could call it the utility or developer side, such as Whisper Valley. That is a planned community in Austin, Texas, that is geared towards being the most eco-friendly planned development community there is. So each house is hooked up to a district heating system that is driven by geothermal heat pumps. And then there are companies like EggGeo that actively install and teach and help people learn about geothermal heat pumps. Now, I've spent a lot of time talking about geothermal heat pumps, but that's not actually one that I want to highlight here, because I think geothermal heat pumps are something that is not as applicable to the oil and gas industry. Of course, there is drilling, there is trenching, there is piping and plumbing. So there's a lot of work that goes into geothermal heat pumps, but I think that there are more applicable areas in these other 4 utilization types. So I'm just going to block that out for now, and we're going to focus in on these other 4: heating, cooling. Cooling can be through absorption or adsorption, binary fluid steam, and direct flash steam. One of the first ways that you separate these are by their temperature. Direct use heating really takes place in that 100 to 300 degrees Fahrenheit range. At 100 degrees Fahrenheit, you can warm and cool buildings. When you get up to something like 300 degrees Fahrenheit, you can start running dehydration processes. You can get even hotter and utilize heat directly for something like hydrogen generation. But in general, and what I think is most relevant here, is looking at that 100 to 300 degree Fahrenheit range for direct heating uses. If you have more of a cooling need, such as down here in Texas, the majority of the time we need cooling as opposed to heating in our houses. In this situation, you can run an adsorption chiller or absorption chiller, depending on the temperature range, and you can produce cooling from your hot water. These often run anywhere from 150 degrees Fahrenheit up to 300 degrees Fahrenheit. So this is an application that could be used somewhere like the Austin Chalk, somewhere like the Haynesville, really many holes along the Gulf Coast that are any amount of depth in the 7,000 to 10,000 foot range. You're probably going to be hitting these temperatures. And that's an opportunity to potentially produce cooling if you're close enough to a cooling demand location. I think what most people think about when they discuss geothermal is electricity generation. These electricity generations are either through a binary fluid system or a binary power system, where you are running heat, you're producing your hot water, you're taking that hot water and you are flashing another working fluid into steam. That steam is spinning a turbine. This can occur anywhere from 200 degrees Fahrenheit up to 350 degrees Fahrenheit. There are some systems that are starting to look at 175, even 150 degrees Fahrenheit, but those are new innovations, so I'm not gonna harp on those too much. As you get hotter temperatures and high enough flow rates and high enough pressures, you can start running what is a direct steam system or a flash steam system. So if you're producing water that it's steam saturated water, or it's partially steam, and depending on the pressure, You could produce it as a fluid, run it through a flash chamber, which drops the pressure and flashes that to a dry steam, and then use that steam to run a turbine. Now, this is really high temperatures. It's really, well, where are these located? We'll work backwards this time. These high temperature systems, or these flash steam systems, are often located in volcanic settings such as the Cascades, or in large scale extensional settings such as the Basin and Range. These areas are really more traditional geothermal focused. The direct or dry steam systems are only found in high temperature subduction zones in volcanic arcs, and flash steam systems are rarely found outside of volcanic arcs. There are some flash steam systems in the Basin and Range. Really what is most relevant to the oil and gas community, and I think what is most relevant for worldwide ready to go energy production, is binary systems and really the direct use applications of heating and cooling. These three types are found pretty much in every sedimentary basin at some level. Sedimentary basins such as the Gulf Coast has opportunities for all three. East Texas, opportunities for all three. The Williston Basin, again, all three. And the Raton Basin up in Colorado. If you remember, looking at that heat flow map, there are areas outside of the Western US that have relatively high heat flow. Those areas are areas of potential electricity production, but more importantly, they are very prospective for heating and cooling. What about the technology readiness level for all of these? I want to make this point very clear. All of these technologies have been proven. They're all technically feasible. All of them work. Many of these have been technically proven in oil and gas co-production. But to date, there are no commercial oil and gas co-production projects running in the US. The commerciality of these is really location dependent. What that means is that the commerciality of any given system is a function of the resource available and the market demand for that resource. And right now, we don't see any of those in the oil and gas world. We'll talk about that in a bit. There are active research projects, several that just were awarded and funded by the Department of Energy, looking at producing geothermal electricity or geothermal heating from oil and gas wells. Those include areas like Oklahoma, the San Joaquin Valley in California, a area in Nevada, and also the Austin Chalk right here in our backyard in Texas. So there's a lot of different areas and a lot of different active research going on to continue to make that technology readiness from a technically feasible standpoint into that commercially feasible. And I wanted to give some examples of where these projects are occurring. So direct use heating is occurring in the West at Klamath Falls, Oregon. We've seen a picture from there. The city of Boise, Idaho. We'll be looking at a picture from there in a little bit. Chena Hot Springs with their adsorption cooling. We talked about the Rocky Mountain Oilfield Testing Center. And there are companies that specifically focus on low temperature binary organic Rankine cycle and other systems to produce electricity from these low temperature fluids. One such company is Access Energy. And of course, those flash steam and direct dry steam systems. Lardorello, we've already looked at a picture from there, and Calpine, which some of you may know as the natural gas producer, they're actually one of the largest geothermal companies, owning and operating the geysers through one of their subsidiaries. So the geysers geothermal system is the largest installed capacity geothermal system in the world. So I just have a picture here. So give you a second. I'm going to grab a drink. If you want to do a screen grab, go ahead. So let's look at this at another viewpoint. When we're talking about geothermal systems, we really look at three ideas. We're looking at direct use, so that direct use of the heat, binary power systems that can generate electricity through taking the heat from those resources, converting it to power through a lower temperature boiling working fluid, and then flash systems. That is flashing that produced fluid directly to steam, running that through a turbine. These systems really are all driven by two factors: temperature and depth. You can see a very high geothermal gradient, 100 degrees C per kilometer. If you have that kind of gradient, you are probably going to be able to produce a conventional high temperature flash geothermal system. Depending on where that resource is, maybe you just want to do a binary system. If you have a lower geothermal gradient of 50 degrees C per kilometer, you probably have direct use capabilities and maybe some binary capabilities. And I forgot to mention, this line here is really that, more or less, that technical feasibility range and commercial feasibility. So once you get past a certain temperature, we can start thinking about producing EGS. It's really technically feasible. We can drill there. Can we actually produce from there? For something that's the global average geothermal gradient, right here at 20 degrees C per kilometer, according to this chart, we don't really have anything that is economically viable. Hot sedimentary aquifers, oil and gas co-production, maybe those will work, but they're not really in an elevated thermal regime, which makes you wonder, are they going to be economic to produce? Are they going to be economic to target for a business? Well, hopefully through the course of this discussion, we'll make the case that there are certain situations where those should be targeted. And I do have one more figure. It's not the best. I really like this chart because it shows the expansive nature of geothermal energy, and really what this is. It's geothermal energy uses, but really this is all industrial heat uses. So when we talk about geothermal, most people think about power production, which is just right here. There are all these other uses for geothermal energy. There's low temperature uses, such as bathing, snow melting, aquaculture, concrete block curing. But then there's also higher temperature uses like lumber drying, cement and aggregate drying, creation of biofuels, refrigeration, and, as I said, even hydrogen production. So there are so many different uses for geothermal. It really is a matter of knowing what your resource is and then finding an applicable use for that thermal energy. So now what we're going to do is we're going to walk through a few more examples of those four types of geothermal energy. The first one being that direct use. This one being a heating heating application. Oftentimes when we're producing geothermal direct use energy, at a multi-user scale or a district heating scale, this will be run by either the public works, this could be an industrial park, or it could be a planned community. So here we're talking about geothermal direct use in a heating sense. This example that I'm giving is from the city of Boise. So the city of Boise, right here in this map, what you see on this map are different pipelines, and then the beige spots are different buildings that are heated by geothermal energy. There are spots that have wells, both production and injection, more production wells, and then the piping that kind of goes all around the city. What does this look like? I don't need to take that long of a pause because I know you can't answer me. But to me, this kind of looks like natural gas going around a city through the piping. So that way everybody can have their heating or their gas for their stoves. This is also reminiscent of my time in undergrad when I would be in my dorm room and there would be radiators. And in Southern Illinois, there was a period during the winter where for some reason it would get up to 70 or 80 degrees in the middle of December or the middle of January every year without fail. We were on a campus-wide district heating setup that was all run by the university's coal-fired power plant. Because we were on this district heating system, those 2 weeks, we didn't have access to cold air. We only had heating. We had no cooling. So those 2 weeks, we were always sweating when we were inside, or it was weird because everybody had their windows open. So this is a situation where I don't know why I just said that story, but this looks very reminiscent of building out these public works that we already have in our cities. The only difference is now, instead of thinking of natural gas infrastructure and passing around natural gas to all of our homes, what we should be thinking about is hot water infrastructure and how we can pass around heat to all the homes through a new transport mechanism, water instead of gas. And we can also have direct use in isolated or remote settings. These I would call one-off settings. The picture here showing something like you've got a very open area. Admittedly, I think this is from Yellowstone. So we've got this big, large area, no real infrastructure built around it. So what do we do in a situation like that? Well, we can build direct use needs in that location. We can build a greenhouse. We can build an ice museum. And that's what we show here are those pictures of greenhouses, again, from Chena Hot Springs. So Chena Hot Springs utilizes their low temperature resource to keep their greenhouses in a productive temperature zone year round. And they have enough flow rate to actually run an absorption chiller that has an ice museum that is now up year round. I really encourage you to go online and check out the Chena Hot Springs Ice Museum. There are some world famous ice sculptures in there, and it is a very, very beautiful place if you ever get a chance to go visit. So let's move a little bit further on now onto the binary power generation. This is a schematic diagram showing how that process works. So you've got wells. These are the wells here, specifically a geothermal well. Think of that as your oil and gas well post separation. So you're producing hot water. So this is kind of on your down This is in your saltwater disposal, your wastewater, after you've already separated out the oil and gas. That water has heat in it. That heat gets exchanged through a heat exchanger with a working fluid, this binary liquid. That binary liquid has this lower boiling point. So this could be a refrigerant like R134A. It could be an organic, something like an isobutane or an isopentane. They are naturally in a gaseous form at atmospheric temperature and pressure. Those will boil when you start heating them with that geothermal fluid. Once they start to boil, that vapor pressure is under pressure. It flashes into the steam, essentially. That flashing spins the turbine. That spinning turbine generates electricity. The electrical power goes off onto the grid. And then you send that through a condenser to then do it all again. That condenser ultimately has some type of cooling system over here that helps recondense that working fluid back down so that it can keep doing that process. After you've produced that water, ultimately that just goes right back into your disposal system and goes wherever it would have gone originally. Where are binary power generation systems occurring? Well, these are the ones that are being demonstrated in oil and gas settings. So this one is from Mississippi. This is a project that Denbury did with Electrotherm, installing a 25 kilowatt machine. You can see the size of this machine. Two guys here, I don't know them personally. I would guess they're somewhere in the range of 5 to 6 feet tall. And this is just a regular trailer here to give you a rough idea of how big this is. So 25 kilowatts. This is something that you could set up, hook up to a single well. The example here on the left, this is the Steamboat geothermal power plant in Reno, Nevada. We've got a line of trucks here for scale. This is 84 megawatts of electricity. So at 84 megawatts of electricity, this is a much larger footprint, but it's still, relatively speaking, if we were to compare it to something like solar or wind, this would still be a relatively small footprint. But this is the other point here, is that for binary power, we can go from wellhead size and 25 kilowatts, which is really just going to offset some of your current energy production, all the way to 84 megawatts, which would be on the order of powering anywhere from estimates of 50,000 homes to 100,000 homes, depending on how much power you use. So binary power systems really are used in a significantly large scale environment if the resource is there. Now, moving up even further to that steam power generation. For a steam power generation, you are producing that hot water. That hot water coming from the reservoir is still somewhat pressurized. So it may be coming up as half water, half steam, something in that realm. So you've got a water saturated steam that you're producing. That is run through a separator. This would then be the high pressure steam entering the turbine at a high pressure location. The water is dropped into a separator. Oftentimes this is a flash chamber that will take this water. It will drop the pressure, and that drop in pressure flashes the water into steam. Now it's a low pressure steam. So that low pressure steam goes into the turbine. So you almost get two effective inputs of energy to spin that turbine. And by doing that, you get an increase in efficiency you get an increase in electricity generation. That electricity ultimately is generated, goes off to the grid. And now your condenser, this is now condensing that produced steam back into a liquid, and any water that didn't flash, and now the steam that has been condensed back down, that ultimately gets returned into the reservoir. What are some examples of steam power generation? Most of these examples are in high temperature systems, in volcanic areas, subduction zones, really tectonically active settings. This example is the Nesjavellir power plant in Iceland. This power plant specifically, so there's a few different cooling towers that you see, and there are no cars or anything in here to give you that viewpoint or that scale. But these little huts here, within those huts are the wellheads. So these are wellhead huts so that the wells don't freeze over during the winter, in case anybody remembers anything related to that. And then these are workshop buildings that gives you kind of a scale and an idea of the size. This power plant is a 120 megawatt power plant and 100 megawatts of thermal energy. So this is both that electricity generation and also direct heating generation. For 100 megawatts of thermal energy, that equates to 600,000 barrels of water per day of hot water. So that's a lot of hot water. So that is the geothermal power and examples of geothermal power. I'm hoping by now you are convinced that you want to get into geothermal, or at least start helping partake in the geothermal industry. But you might be wondering, what's the catch? Well, there are important aspects here that we need to discuss. As I said earlier, really the two main factors when we talk about geothermal energy is temperature and flow rate. This chart here was made based on the Future of Geothermal report that was published, work done by MIT and a large collaboration consortium group. This was done back in 2006. On this chart, you see several different lines going from, these are fluid temperature lines. On the bottom, you've got the kilowatts of power that you're going to generate. And then on the y-axis, you have either barrels per day on the right or gallons per minute of flow on the left. So for any set flow rate in barrels per day of hot water, you can just go over to that temperature that you're at. For simplicity, let's go to this 225, just about boiling, and about 16,000 barrels per day. 16,000 barrels per day seems like a lot of water to be producing. At that flow rate and that temperature of 225, which we may see in East Texas, we may see in South Texas, 225 is not that hard to get to, but that 16,000 barrels a day, that may be difficult. For that, we can get 500 kilowatts of electricity. If you just jump over in temperature to this 275 degrees Fahrenheit line, so for that extra 50 degrees in Fahrenheit temperature increase, you double your power for the same flow rate. So here it's important to realize flow rate matters. You need high flow rates, but every single degree of temperature gives you a significant amount of additional energy that you can produce. Here, those 50 degrees of temperature increase double your electricity production potential. Now, this is obviously just a high level first look at what you may be able to get. Is it worth going further? So it's important to point out you need high flow rates, which means typically you need bigger wells. And there was a comparison that one of my colleagues made the other day. For 30 barrels of oil, you need 14,000 barrels of water at a power production temperature in order to equal the same amount of power. So 30 barrels of oil versus 14,000 barrels of water. The price difference there for those 30 barrels of oil, if that's at $60 a barrel, for that water, we're talking about pennies per barrel of water. So in order to get those high flow rates, really you need as big of wells as possible. And it's important to point out that there is significantly lower power density than a barrel of oil. These are going to have higher upfront costs because you have to drill those wells, you have to produce all of that water, and then you can build up that power plant. This is an area where if we already have wells because of oil and gas drilling, we've already taken care of a lot of that upfront cost. And I wanted to get into this idea of future wells, which is going to be transitioning us into how does oil and gas fit into all of this geothermal talk. It's important to think about these next generation of wells. They're going to be expensive. They're going to be drilled deep. They are not proven technology. But the idea here, so let me walk you through this. The idea is that we've got a typical Haynesville shale gas well, drilled to about 3 kilometers depth, and then you've got your hydraulic stimulation. The energy equivalence that's produced from one of those wells is about 10 megawatts of electricity. For a conventional geothermal well, those are drilled to about 2 kilometers and 230 degrees Celsius. Those are about 7 megawatts of electricity per well. So these are relatively similar, different scenarios, different settings, but kind of similar in terms of energy density value coming from an individual well. Right now, a big push is for engineered geothermal systems. Engineered geothermal systems are targeting 3 to 5 kilometers depth at temperatures typically 150 to 200 degrees Celsius. Those are depths and temperatures that we are actively drilling in the oil and gas industry. These are also then going to need to be fractured or hydraulically stimulated. And this is going to have to take place oftentimes into basement rock. So hydraulic stimulation in granites. And the future idea is super hot rock or super hot EGS. These will be wells drilled to greater than 5 kilometers at temperatures of 450 degrees Celsius. The idea here is that by going into those temperatures and pressures, we're jumping into the supercritical realm for pressure temperature for water. By doing that, we get a 10-fold increase on the power production or the power density of those wells. And then a well could be 40 to 50 megawatts of power. So the equivalent of 5 shale gas wells for a significantly decreased amount of drilling. We could say 10 kilometers of drilling for 50 megawatts of power versus to get that same 50 megawatts, we would have to do 15 kilometers of drilling. So the future of geothermal is really expanding upon the ideas of the difficulties that oil and gas has started to overcome in unconventionals. So let's say this is a bit of a sidebar. Let's say you have high enough water production, high enough temperatures. What are those next steps that you would have to do before we start talking about other stuff? What else would you have to think about and consider if you wanted to start looking at geothermal? You do have to consider the well integrity, the age, the existing corrosion, and the flow rate, temperature, and pressure history. For something like that, if you are going to increase the flow rate, how is that going to potentially cause more wellbore integrity issues? The fluid chemistry, and the TDS. Can you change out the tubing in the well? Can you change the flow rate and do that with minimal wellbore risk? This really just gets back to the idea of wellbore integrity, because the last thing you want to do is take this old well and start pumping it like crazy, and then ultimately you get a wellbore failure. Induced seismicity, this is a big one that we always have to talk about. With these geothermal wells, we are going to be producing higher flow rates, potentially. That means we're going to have more disposal. Are you set up for that? Where are you going to dispose this additional flow? If you're not going to pump more and you already have a disposal plan, then great. And what about reservoir pressure management? One of the biggest issues with these low temperature systems is the parasitic load from pumping. If you have to pump more, you're going to have greater parasitic load, which means you're going to have a lower net energy production. So you really need to consider how can you keep good pressure management for your reservoir so that you can continually produce from it. Or are you in a mature gas reservoir that is extremely depleted in pressure? If that's the case, it's probably not going to be worth it to try and explore it. But if you have the temperature and the flow rate still, maybe it's okay. And then another thing to discuss is it's going to take a different financial model. You'll need to run the financials to determine the minimum IRR or ROI or simple payback, whatever your preferred financial metric is. These are just things I wanted to include here because you may already have the flow rate, you may already have the temperature, and now you're already thinking like, how do I make this happen? Now you have some steps that you can do. You can pause the video here. You can go start thinking about this, send me an email. We can talk about it and keep those juices flowing, and then restart the video and let's finish up. So for all of you that kept going, I'm glad you're still here. For those that paused the video there, welcome back. Now, how do we leverage oil and gas to advance geothermal? The first step is exploration. We need to leverage data, techniques, and workforce to develop more geothermal. What this means is data cleaning and characterization. Many of my studies over the past 5 years, most of them over the past 10 years, have focused on oil and gas data. All of these data points are well log headers and BHTs from well log headers. Having good, clean data, and more importantly, a complete data set is necessary to high grade and find those areas that are most prospective for geothermal energy production. Once you have good data cleaning and characterization, then we run this through a typical play fairway analysis, data analysis, looking at combining those different layers that you need for a geothermal system, that being a reservoir, a structure, the temperature, a seal, running those through data analysis to find the areas that are most prospective for geothermal, now with all of the components you need, not just the temperature. And then run it through a probability map or doing some common risk map calculation. Here, really figuring out, you've made these probability maps, or you've made the play fairway maps. Now the idea is, what areas actually have probability? What are the areas where we are certain? This flow rate here of data cleaning, data analysis, probability mapping leads you to data-driven decision making. This workflow is something that was adapted from the oil and gas industry, and something that the oil and gas industry knows well. So this is an area where leveraging the data, leveraging this workflow and technique, having that done by more than just a handful of geothermal geologists, could drive more discoveries and more geothermal energy production. How does this help, and how does this leverage oil and gas? Well, we could look at prolonging existing assets through this low temperature co-production. The image on the right is from the Rocky Mountain Oilfield Testing Center. That was one area where they were able to continue production and continue it in a valuable way, so that they could get data, they could get more oil, they could get green energy. There are projects that have looked at anywhere from 4,000 barrels up to 60,000 barrels of water per day in temperatures from 90 to 100 degrees C, or 195 up to about 215 degrees Fahrenheit. Those are projects that demonstrated geothermal energy production. They were technically feasible. All of them ran and produced electricity. Depending on the location, that price was competitive with the current electricity market. In some cases, it wasn't. But this is an area where maybe the electricity is just one of those inputs. If you're able to prolong your field, maybe that extra oil production ultimately makes the whole project valuable. And then you have a renewable energy that you're getting that is decreasing your carbon footprint, which is important. There are several projects that were recently funded. We talked about those earlier. Those, hopefully at CarbonExpo 2023, we'll have some updates on that I could talk about. So this could be anywhere from a single wellhead system for enhanced oil recovery, or it could be high water cut wells. This example down here is from the Williston Basin. This is actually these are water production wells that are taking in, they're water production wells that are for a water flood. So these have 100% water cut at a high temperature, at a high flow rate, that are now pulling off electricity generation before they're going to their original use case, which is going into a water flood. And for these projects, we're looking at 25 to 250 kilowatts of power generation. And we could go bigger. Can't really go smaller than 25, but this is an example of, again, we can scale power generation depending on the resource potential. So this is a modular, scalable system that can help really any oil and gas company. And one thing, as I was preparing all these slides for CarbonExpo, one thing I was thinking about was legacy field repurposing, the idea of the dawn of the counter stream. What we could do is we could start flipping that idea where renewable energy or carbon capture and sequestration becomes the primary revenue driver. That becomes that first input of money. And then the hydrocarbon that you're getting if it's 1, 2 barrels, if it's a 98% water cut, 2% oil, that 2% is really just a byproduct now. But you're still able to utilize, repurpose that legacy oil field and now repurpose it in a way that is counterstream to what we've been thinking before. Another step is engineering solutions. This is a schematic example from the deep earth energy production setup in Alberta. It's on the Canadian side of the Williston Basin. Does that look familiar to anybody? It really looks very similar to unconventional engineering and unconventional production. This is an area where all of the petroleum engineers, all of the technical folks in oil and gas could very easily transition into this EGS kind of production. But then we also have other more challenging problems. Two examples I'll give is Ever Technologies, where we've got these lateral wells that are connecting in the subsurface and drilling multiple multilaterals, all coming from one or two topside vertical sections. And then we also have ideas of drilling a single well that ultimately splays out. So these are new well designs, and more importantly, they're targeting high pressure, high temperature, 5 to 10 kilometers, 400 to 500 degrees Celsius. These are in the basement, so they are considered hard rock, but because of the high pressure and high temperature, they're also teetering on that brittle ductile transition where you're starting to get quote unquote plastic rocks. They start to move a little bit. And in some respects, this is very similar to the early days of unconventionals and really understanding when a shale really isn't a shale and what shales can be hydraulically stimulated, what that shale versus that siltstone, what that mineralogy is, and how that ends up ultimately being stimulatable or not. This is where we start to need more input into geothermal and more real just long-term experience understanding how can we develop these stimulation techniques and technologies and ideas to really break the rock and to produce these newer resources that we want. And now this thing, I want to bring it back. I want to bring it close to home. We've been talking all these big ideas, but we haven't really focused on Fort Worth, or we haven't focused on Dallas. We haven't focused on the those kind of legacy unconventional or legacy conventional old oil fields. So what about those? What about the old depleted cold areas? What about Corsicana? Or what about Conroe outside of Houston? And of course, what about Midland? If any of you were looking at the map back when I had that map open, the Permian Basin's cold. I will unapologetically say there is no natural geothermal system in the Permian Basin. Well, if there isn't a geothermal resource, let's just make one. If we combine all of these different ideas, and this is what we're doing, is we're building a synthetic geothermal reservoir. Let me just walk you through this real quick. We can use the subsurface as a battery, as a heat battery. So we can pull cold water out, We can heat that cold water using the excess concentrated solar power that we have in West Texas. We can take that heat and we can pump it back down into the subsurface and store it there. When we need to produce that power, we can pump out of that hot well, produce that hot water, run that through a typical turbine, a typical generator, produce green power, send that off to the grid, and then we eventually cool it off and pump that water back down into the subsurface. In this way, we have essentially taken something that is a intermittent renewable green energy source, such as solar power. We've taken an area that doesn't have geothermal, such as the Permian. We've combined the two to make one base load green energy power source that now is a potential power source to continue the energy prosperity of an area such as the Permian. So with that, let's talk about a few final thoughts. Geothermal can be categorized in many ways, but really, geothermal energy is everywhere. So we've talked about 4 different utilization types, but I want you to leave this conversation knowing that geothermal is everywhere. Whether you want to use it in your house as a ground source heat pump or a geothermal heat pump, or whether you want to build a power plant on the side of a volcano, or whether you want to make your own synthetic geothermal power plant in the Southwest of the United States. You can. And you can do that by using and getting buy-in from oil and gas. We can do these non-traditional geothermal, these different ways of utilizing it. This is the way of the future, but it is going to require buy-in from oil and gas. This is going to require the knowledge and expertise to process automate, to reduce cost. It is going to require the workforce to achieve the scaling up potential and the goals of scaling up to this large gigawatt scale power production. And ultimately, it's going to require investment from oil and gas and acceptance of a new business model. One phrase that is being used a lot in geothermal is use the earth to save the earth. Geothermal is that foundational energy. The subsurface is that foundational battery that we can use to build a foundation for a green energy future. As we've been talking, we have combined intermittent renewable sources of solar power. We could use wind power. We've pulled hydraulic stimulation technologies from unconventional oil and gas. We've combined all of the infrastructure that midstream uses, all of the piping, all of the house hookups. All of this we can combine together. Ultimately, it's all driven by the energy and energy storage that we can use in the earth. And with our ingenuity, we can apply it everywhere. So if you need help, if you want more information, I would encourage you to give me a call Petrolern. As I said earlier, we look at this stuff. Petrolern has integrated workflows that provide unique data-driven clean solutions. We do everything from geospatial data analytics using AI and machine learning. We use that to produce new play fairway analyses, and we can apply that, and we have applied that to filling in gaps that we see within geothermal and within the future energy infrastructure, that being high resolution 3D and 4D thermal hydromechanical modeling, specific tools developed for quickly and efficiently analyzing legacy resources, ConvertDeck is specifically for looking at conversion of oil and gas wells to a geothermal resource and a geothermal use. And then also ideas like the synthetic geothermal reservoir, basically applying both traditional and innovative ideas to power plant design. This is something that we can do as simply as a quick 1 day look at your data and tell you if you have a potential resource, or this can be something that we are actively doing 4 to 6 month long deep dives for investment grade reporting. I'm going to include this. If you want to know where any of those pictures came from, or you want to have any specific resources to go and look at, here it is. Feel free to do a screen grab. I'll give you a second. And with that, I'm going to end. Thank you very much for your time. If you have any questions, I would encourage you to ask them now. The problem is you're not there. I'm not there. Well, I may be there. I don't know if I'm there. But there is my email, and you can email me your questions. And I encourage you to email me your questions right now. But otherwise, I've enjoyed this. Thank you to Dwayne and his team putting on CarbonExpo. And I look forward to connecting and speaking with you all in the future. Thank you.